In this lecture, we look at buoyancy. Buoyancy is described by Archimedes' Principle, which states that an object that is fully or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid that object displaces. Let's see how that happens. Let's look at our block of water in our pond. We still have the same forces as we saw before. We have a force upward, a force downward due to the pressures of the water above and below the block, and then we have the weight of the water itself in the block, m water times g. If we place the block of water with a block of air instead, or basically with nothing, then the weight goes away, and all that's left is the difference between F up and F down, and that net force is upward, and this is what we mean by the buoyant force. So the difference between F up minus F down is this mass of the water times g. So if we replace the block of aluminum, replace this empty block with a block of aluminum whose density is greater than water, then we have, now we have a new weight for the block of aluminum, and it's bigger than the weight of the water, but the buoyant force is still the mass of the water times g. But also, the weight of the aluminum block is bigger than the weight of the water, so the mass of the aluminum times g is greater than the mass of water times g, so the block will sink, which shouldn't surprise you. What is the buoyant force on a 10 centimeter radius helium balloon in air? In this case, the air is the fluid that is being displaced, so F buoyant is equal to the mass of the air times g. And to find the mass of the air, we have to take the density of the air times the volume of the balloon times g. And the density of air is 1.21 kilograms per cubic meter times the volume of the balloon, which in this case is 0.004 cubic meters for this 10 centimeter radius balloon, times g. If we plug in the numbers, we find that F buoyant is equal to 0.005 kilograms, or 5 grams, that's the mass of the air, times g, or about 0.05 newtons. Note that if the weight of the balloon plus the helium inside the balloon is more than 5 grams, the balloon will not float. Let's look at an example of loading a river barge. Your barge floats on a river. When it is empty, it displaces 30 cubic meters of water. Its maximum displacement is 100 cubic meters of water. That is, if you're pressing the hull down to the point at which water comes in over the side, it would displace 100 cubic meters of water. You have a customer who wants to transport 80,000 kilograms of wood. Can you load it onto your barge without sinking the barge? If the load's weight is greater than the weight of 70 cubic meters of water, your barge will sink. Rho of water is equal to 1,000 kilograms per cubic meter, so 70 cubic meters of water has a mass of 70,000 kilograms. So you say no. But your customer comes back and says, wood floats, so it'll be okay. Is he right? Well, no. Sadly, the wood is not displacing the water. So if you were to put the 80,000 kilograms of wood into the barge, the weight will push the barge's hull down until the water flows over the edges of the hull and fill it, and the barge will sink. The wood might end up floating on top of the water, but your barge won't.